In this chapter, we will be using calculus as a tool in curve sketching. In this lesson, we will be looking at oblique asymptotes.
All right, hi everybody. So in this lesson here we're going to talk about oblique asymptotes. Now, probably need to explain the word oblique just really quickly here. Oblique simply means that it's not going to be horizontal, it's not going to be vertical, it's going to be off at an angle like that. Now, oftentimes people want to call that a diagonal asymptote, but actually that's not quite the right word. A diagonal is what happens when you take 2 points on a polygon and connect them. So this line is now diagonal to this polygon here. But if you're just talking about a line that's, okay, a straight line that's not vertical, that's not horizontal, then that's called oblique. Okay, so this is what we're going to take a look at in this particular lesson here. Now, it should be noted though that this is still just the beginning of the way, or the analysis of asymptotes here. These occur in rational functions where there is no horizontal asymptote, okay? So when there's an absence of a horizontal asymptote, you're very likely going to have an oblique asymptote. And just so that you know here, it doesn't have to be a straight line. If you get, for example, if you get a cubic over a quadratic, note that the difference in the degrees here is 1. That difference in degrees is going to be is going to lead us to a linear asymptote here. However, if you had a cubic over a linear, then the difference in the degrees is 2. And as a result, you would have a quadratic asymptote. And I know that probably sounds like a horrible thing for me to say, but yeah, you could have an asymptote. Let me just draw one real quickly. You could have an asymptote that looks something like this. Okay, where some other function, let's say, comes up to it. Let's say it comes up and then it swoops along, and then as you go along, it gets closer and closer and closer to that quadratic function. So it's asymptotically related to that quadratic. If this was a quartic over a linear, then your asymptote would be cubic. Okay, so the difference in degrees means that you can have asymptotes of any degree. Now, just to allay your fears here, we're not going to get super complicated. We are only going to look at linear asymptotes. So we're going to look at the situation here where you get like a cubic over a quadratic over a linear, which is actually quite simple. But we're only going to look at situations where the degree difference is just 1. So we are just going to get linear functions here, linear asymptotes. Now, I can explain to you how that all works, but the easiest thing to do actually right now is just to jump in and take a look at an example. So we're going to take a look at one here, and I'm going to give you 2 different versions of the function as we go through it, and then later on we'll just take a look at a function itself, and I'll show you how you would analyze it. Okay, so for our first example here, we're going to find the asymptotes of the function f of x is equal to x plus 1 over x. And if you were to put those together, if you were to add this expression to this expression right here, you'd get x squared plus x plus 1 all over x. And so we're just going to take a look at these 2 representations of exactly the same function. We're just going to be right up front with the way this one function can be represented here. Now, first of all, we'll back up just a little bit here. Okay, first of all, notice that we've got a non-permissible here at x is equal to 0. Okay, and it's an essential discontinuity. Okay, essential discontinuity. Meaning that it's present there at the end. After I've tried simplifying the whole expression, I can't cancel that out. That x is stuck down there. I am stuck with it. So I am stuck with this x down here, meaning that I cannot allow x to be equal to 0, because that leads to a non-permissible. And that becomes our vertical asymptote. So that's pretty easy to find. Okay. Now we're going to take a look at, or we're going to look for, I should say, we're going to look for the horizontal asymptote, and we do that by taking the limit as x goes to infinity. So let's just take a quick look at this. So I'm going to let take the limit as x goes to plus or minus infinity of this function right here. And notice the way that I would normally do this would be to multiply by the highest degree. Now normally I would multiply by the highest degree in the denominator. So I'll actually do this twice here. What's been done here is this function has had its numerator and denominator multiplied by 1 over x squared. Okay, and when we did that, when we distributed that through to all three terms in the numerator, I got 1 plus 1 over x plus 1 over x squared all over 1 over x. And when you let x go to either positive or negative infinity, each one of these things disappears and goes to 0. But that leaves me with 1 over 0, which is an undefined, which is it does not exist. Okay, whoops. Another way that we could have done that and gotten the exact same result is I could have multiplied by 1 over the largest degree in the denominator. I could have done it like that. And that's normally the way I personally would have approached this. Okay, so I would have probably gone x plus or minus infinity, and I would have multiplied x squared plus x plus 1 over x. I would have multiplied that by the highest degree in the denominator, 1 over x, 1 over x. And this would have become the limit as x approaches plus or minus infinity of x plus 1 over x all over 1. And you should recognize that from one of the previous expressions that we have for this function here. Now, as x goes off to infinity, 1 over x is going to go to 0. That's clear. But then I'm going to be stuck with this x plus 1, and as x goes to infinity, that x is also going to go to infinity. And so what's going to happen is this function is just going to get larger and larger and larger in both directions, the positive direction and the negative direction here. And so as a result, the limit here does not exist, and we know that there is, in fact, no horizontal asymptote. But notice what happens when we take the infinite limit. Notice what happens when I did it that second way right here, and I look at this expression right here. Now this was all over 1 when I wrote it before, but I want you to notice something about this. What happens here, as you let x go off to either positive or negative infinity, is that the function itself can be broken up into two bits. You've got this linear function right here, plus this expression right here, this 1 over x, this little rational here. Now, the line isn't causing me any kind of difficulty at all. It's just a line. It's got a slope of 1, y-intercept of 1. It's just going off like this. So what's happening here, if you want to think of this graphically, here's my coordinate plane. My function is doing this. It behaves a lot like this line does, which is just going to look like this. Okay? And as x gets really, really large, you're going to have this function plus this little bit right here. So it's basically getting closer and closer and closer to this dotted line here. But this piece here gets smaller and smaller and smaller as x gets larger and larger and larger. So as you go further and further and further to the right, the original function is going to be equal to this line plus a little bit. And as you go every step forward, it's going to be plus a little bit less, plus a little bit less, plus a little bit less. And so that line is going to get closer and closer and closer, or the function, I should say, is going to get closer and closer to this dotted line. So as a result, what's basically happens here is as you take the limit as x goes to positive or negative infinity, this piece here disappears, and you are left with that linear function. Now, this is not a great way to take a limit, by the way. Like what I just did there was not cool. Because I left the x in there. It's really only this x that I dealt with here. But I'm just trying to make a point here that the function behaves like this function right here. The overall function behaves like this little linear function with this little bit left over that gets smaller and smaller and smaller as x goes to infinity. And so the overall behavior, as you get further and further away, tends to look just like that linear function right there. Okay? So now, if that makes sense, let's take a quick look at the graph here. Whoops, let's zoom back out a little bit here. Remember that we had that asymptote, that vertical asymptote at x equals 0. And that's what we've got here. And so And when you've got smaller values of x, that's the part of the function that takes over. When you've got x plus 1 over x, when you've got really small values of x, a really small value of x plus 1 is just going to be a little bit bigger than 1. But with really small values of x, 1 over x is going to become quite large. And so that's why the closer, or the smaller and smaller that x gets, the closer and closer we get to the x-axis, then this term takes over, and that's why this thing shoots off to either a positive infinity or a negative infinity. But when you let x get larger, this piece now becomes less and less of an has less and less of an impact on the value of the function. So it's this part that has a larger impact on the value. And so it just becomes this line plus a little bit, this line plus a little bit. If you go to the right, if you go to the left, it's this dotted line minus a little bit, because that 1 over x will become negative. Okay? And so that is basically how that's going to look. Now there's maybe a little bit more that could be said about the, like, I guess being a little bit more rigorous. Okay? I could write in that if I wanted to define y equals mx plus b as our oblique asymptote, if I really wanted that, then it would be true that as the limit as x goes to positive or negative infinity, if I was to take the original function and subtract mx plus b, if my mx plus b, whoops, I should put brackets around that, if that is my oblique asymptote, then as I go to infinity, that difference becomes 0. And you can see that right here. As we go further and further away from the origin, the distance between the function and that dotted line goes to 0. This is perhaps a little bit more of a rigorous way to approach this problem, but does it really help at this point here? Maybe not so much. I'm going to take a look at another example here and kind of walk you through it. It's going to be a little bit more involved, and so hopefully you'll get a better sense of what it is that we want you to do at this level. Okay, so for this example, we're going to find the asymptotes of this function here, 2x squared plus 6x plus 5 over x plus 2. Now, to start off with, it's fairly easy to identify the vertical asymptote. Okay, that's going to be where this function is undefined, and that's going to be at x equals negative 2. Okay, so that was pretty easy to tell what's going on here. Now, I could use limits to investigate how the function is behaving on either side of that value there, so I can tell whether it's going up or whether it's going down. But for right now, what we're going to do here is I really want to just look at focus our attention on the oblique asymptote here. So we'll come back to that if we have to, if we can't come up with a clean sketch or a fairly rough sketch, I should say, in just a few minutes here. Now we're going to look at our horizontal asymptote, and notice that the degree of the numerator is 1 more than the degree of the denominator, meaning that the numerator here is going to dominate the value of the entire expression as x gets really, really large. Okay? When you start plugging in really, really big values for x into this, when you throw in 1,000,000 and you square it, 1,000,000 millions, okay, this is going to become so big that doesn't really matter. The denominator is going to have very little impact on the value, or at least a smaller and smaller impact. So in this case here, there's no horizontal asymptote, which suggests the presence of an oblique asymptote. And I note that the degree of the numerator is 1 more than the degree of the denominator. So I am expecting, okay, for my oblique asymptote, I am expecting a linear asymptote. Okay? And that's exactly what you're going to get in this particular course here. Now, to show you how this works, what we're going to do, and your approach is very likely going to be the same every time you get faced with this throughout the questions that you're doing in this chapter. What we're going to do is we're going to rewrite this expression, but I'm going to do the division. I'm actually going to perform the division here, and I'm going to use polynomial long division to do it. Okay? I could use synthetic division for sure, but it's not always going to be a quadratic over a linear. Okay? It could very easily be a cubic over a quadratic or a quartic over a cubic, in which case your synthetic division is not nearly so useful to you. So we're going to just do polynomial long division here, and I'll show you how I would set this up here. Remember that when I divide this out, I look at my dividend here, and I look at my divisor, and my goal is to systematically remove terms from the dividend. Okay, I want to at first get rid of this 2x squared. And to do that, with my divisor here, I'm going to use the x, the highest degree term. So to make it look like 2x squared, I want my x to look like 2x squared, I'm going to multiply this by 2x. So when I multiply 2x by x, I get 2x squared. Awesome. However, I'm not done. You can't just multiply this by part of a binomial. You got to multiply by the whole binomial. So 2x also has to distribute to that 2. And so I will have 4x right there. And now I'll subtract. 2x squared minus 2x squared goes to 0. That's exactly what I wanted. That's why I chose 2x there. I wanted that term with the highest degree to disappear. 6x minus 4x is going to give me 2x. And 5 minus 0 is just going to be 5. Good. Now, the degree of the remainder here is the same as the degree of the divisor, so I keep going. I now want to get rid of this leading term in my remainder. I'm using x, and I want to get rid of a 2x, so I'm just going to multiply by 2. And I will distribute the 2 to both terms in that binomial. So 2x plus 4. And I will subtract. 2x minus 2x is 0. Good, that's exactly what I wanted to happen here. 5 minus 4 is going to be 1. And now that the degree of the remainder is less than the divisor, I'm done. Now, technically speaking, I could actually keep going here. Okay, there is a way to keep going, but it does get messy. And just like a lot of your questions where you start dropping the decimal and start putting zeros, this could go on for forever. So I'm happy with this the way it is, okay? Because what I've just stated here is that 2x squared plus 6x plus 5 over x plus 2 is equal to the quotient 2x plus 2 plus, okay, it was this, plus the remainder divided by x plus 2. Basically what we're saying here is I tried to do the division, I was able to get this much of it done, and then I got to here. And I stopped here because the degree of my remainder is less than my divisor, so I wasn't really able to keep going. I mean, I could have, but we choose not to here. And so I needed to add to that whatever that division would have been. So here's my quotient plus the remainder divided by the divisor. And once I know what this is, I know that they're completely equal. Okay, so what have I done? Well, not much actually. All I've really done is just rewritten the original function in this form. But now, when I want to figure out what the asymptote is, I'm going to take the limit as x goes to positive or negative infinity here. And when I do it of this function right here, that is going to be exactly the same as doing it with this function. Because they're one and the same. These two are equal. But when I write it in this form here, it becomes a lot clearer to me that what's going to happen here is that as x gets large, as x goes to positive or negative infinity, it's basically following this line, this linear function, and then I'm going to deviate from that by adding this little bit left over. And the larger x gets, the smaller this whole fraction gets. So this little piece is going to, basically it's going to be equal to this line plus this little bit that gets smaller and smaller and smaller as we go along. So as a result, my oblique asymptote ends up being that line right there, 2x plus 2. My oblique line asymptote is y equals 2x plus 2. Essentially, if you want to think of it like this, it's the quotient. When you do that division, the quotient will end up being your oblique asymptote. So now, what does this function look like? Now, I can't give you a very detailed sketch, honestly, because there's so many other things that we should have been looking for. So this is going to be a very, very rough sketch here. But we knew that there was a vertical asymptote at -2. And now I know that there's this oblique asymptote at 2x plus 2. Okay, so there's my y-intercept here. It's got a slope of 2, so it's going to go here, and then down 2, so it's going to go here. 1, 2, whoops. No, that's right. That's what I wanted here. And then, so my asymptote's going to look something like this. And I know as I go along here, watch this, the way the function works here is as x gets positive, gets large in the positive direction, it's going to be equal to this line plus a little bit. So as you go really, really far this way, it's going to be equal to this line plus a little bit. So I'm actually approaching the asymptote from above. So my function kind of has to look like this. As you go to the left, this is going to become negative. Okay, we're going to go to the negative side of this line. And when we add this here, when you start talking about really, really, like I guess, large negative values of x, like -1,000 plus 2, 1 divided by that, well, that's going to be -2. So it's going to be equal to this line plus this negative value. So it's going to equal this line minus a little bit. So it's actually going to follow it from below. It's actually going to be equal to this line. As you go further and further to the left, okay, large negative values way over here, it's going to equal this line plus that little bit extra, that remainder over the divisor, but that's going to be negative. So it's going to be equal to this line minus a little bit. So it's going to drop down. And so my function really is going to look something like that. Okay, I don't know where the maxes and mins are going to be. I didn't look into that. That's roughly what it's going to look like. So remember how this works. It's all kind of summarized right here. The oblique asymptote is going to end up being the quotient, okay, when you take the numerator and divide it by the denominator in that rational expression. Hope that helps.